All right. So, yeah, warm welcome also from my side. Um, so, I'm happy to be your host today for the book club, Rust Atomics and Logs. So it has been written by Mara Boss. Let me maybe shortly get my setup ready. I like to highlight stuff with a pen. So okay, so here you see a picture of her. I found it on our company website, and yeah, I think she like deserves a lot of credit for us to be here together. And today's topic are the operating system primitives. And well, let's dig into it, I guess. So we will start with a short like motivation and a bit of retrospective, and then we will take a look about what is a kernel, why are we interfacing it to get like a better understanding for the upcoming functionalities. By the way, I hope you like the Dragon. It is AI generated. I did it when I visited a friend on the weekend. So yeah, and then we will really dig into more advanced stuff like the pthread library in POSIX, which was like the basic for a lot of synchronization primitives in the earlier Rust versions. Then we will talk about futex, fast user space. Yeah, I have to look it up to be honest. And then we will see futex is also quite Linux related, how other non-Linux OSs will do. And at the end, we have a summary and outlook and hopefully a nice discussion. And yeah, so the motivation we have today is like, well, I jumped to the bottom. So we want to implement a mutex that does not waste energy, but how can we do it? So that is the main motivation. And if you remember chapter 4, there we did implement a spin lock mutex, which was like waiting in a busy while loop. And well, we could give a hint for the processor. And as far as I understand, this hint helps on some architectures to get your like hyper-threading and so on can be used there. But we really don't want to be too long in a busy loop and wasting energy. So I think for people attending here, the main reason is like we want to have a deeper understanding about a lot of stuff. So in the last week, Chiara, she gave us a lot of cool x36 and ARM assembler instruction to think about. And we saw how these atomics are implemented in assembler. And today it's all about like, okay, what can the operating system do to help us? And yeah, so I read kernel a lot and I felt like, yeah, I have kind of an understanding of it, but as a scientist, I was like, where's a good definition? And like there was something I found really early. It was quite let's say quite an overview. So the kernel is a central component of an operating system that manages operations of computer and hardware. It basically manages operations of memory and CPU time. Its core component of a operating system, and here's this diagram. It shows, okay, it's like an addition, like a layer for us to rely on to write good applications. But I wasn't like I didn't felt too I had hunger for a better, a more profound or more complex definition. So I ended up with this slide. Sorry for that. So here's like a really a simplified structure of the Linux kernel. And when you see here are several, so on the left side here are several subsystems for input-output, like file system and sockets over the network, memory management. And what we're talking about a lot here is like process management subsystems, like thread creation and termination, which was some topic at the beginning. And also, yeah, for us to get it synchronized if we have concurrent applications. So what I liked a lot is like that we got like names in here by the more like complex definition, that it is like a bridge between the user space applications and that we really can use the kernel to efficiently allocate resources, because the kernel is at the end the interface to the hardware, in our case, the processor that needs to manage multi-threads or maybe multiple processors. Okay, so how can we interface with the kernel? And well, when I did some research, I really was remembered how I loved layers, because if you think about it, so for me, I mostly work or coded in this user applications area. So I wrote some games. So maybe I got like a small understanding about this graphics stuff here, like using DirectX or OpenGL. And well, the system components, they are already providing good help. But what we will look at is the C standard library, where we have like functions like pthread create, which is like an extension actually of the C standard library, the POSIX standard, which is implemented under Linux. And the standard library is normally used by us, I say, normal application programmers to access the kernel. And then the kernel, it provides a lot of system calls and so on. Like, that is like the architecture we're dealing with, and also like maybe the knowledge we can build upon. Yeah, and the nice thing in Linux is like you can really have like a safe direct syscall into the kernel, so that's not working in other operating systems, because there may be breaking changes, and you really should use the standard library the OS vendor provides, or in the Windows case, the Windows 32 API. Yeah. Okay. So the POSIX library, so that was or is the like first more technical paragraph, or more near to the implementation, where we have a lot of functions. So I just listed them here to like get a kind of overview how much it is. And we have like 3 C functions for different types, like the mutex. We have an initialization, and we can also have some configuration for recursive locking or to destroy it. So we really have to use this init and destroy methods. And then we have lock or try lock messages, and also unlock. I'm not sure why it's missing here, to work with the to lock and unlock the mutex or the read-write lock. And also the POSIX standard provides condition variables, which can be signaled, and or which can be like, one can get signaled, or everything can get broadcast. And yeah, so with all of this, we come like to the interesting part. How can we maybe use the POSIX pthread libraries to wrap this in Rust. And as you can see here in the code, we are really working on specific operating systems. So in this case, we have a mutex log, and as external function. So we can use this libc type, and then this function that is provided by the libc. So it's a crate in Rust. And then in the type we use we could use like an unsafe cell to just store the mutex, because it, yeah, as I said, it will be mutated by those functions. So I'm a bit confused. I'm missing a code example here. Like what you can think of is like, here's a small type, a struct with just holding this member to expose us a mutex type. Yeah, I think you know what I mean. Yeah, but then there will be challenges coming up, like we have to move, or in Rust, a lot of variables are moved, like there's a move by default behavior. And because this pthread library, it has all this, it's like a legacy C library. And yeah, when you work with C, you really have to check the implementation, because nobody can really know if there may be also an outside pointer pointing to the mutex. And well, when we have like a pointer that somehow refers to memory in our own object, and we move it, then these pointers are invalidated. And yeah, this pthread mutex t, it's really not movable, but we have some options. Therefore, we can use an unsafe interface, and well, I don't like it, because God, writing with mouse. Safe API, that is the that's what I like about Rust a lot, and so that's not an option for me. Or we could take the ownership away with just using a stud pin. And maybe there's also another solution. And there's a code I was searching. I thought I would have it on the slide before. So a workable solution is really like we can add like around the unsafe cell, which is our mutex type, we can add a box. And now yeah, we move the mutex onto the heap. So for those who are not too much into data-oriented programming, that's often like an overhead that is hard to predict, because we now need an allocation, and the operating system has to provide memory. We cannot use const functions in Rust, which is like a problem when we want to use to store like a static mutex, for example. And like we have a case, and we will see this a bit later, where the studmem forgot on the type. It can lead to actual undefined behavior. And so what means overhead in the worst cases? So that's quite cool, because Chiara talked about this in the last chapter. So you may get a cache miss because the mutex is somewhere on the heap, and maybe we didn't use it for some time. And this cache miss, it's really waiting for ages, like microseconds, which is really long. And yeah, so have a look at the caching subsection. That was quite interesting in the last chapter, to get a feeling about that. But now let's get back to this behavior. So drop in combination with stoop mem forget on the guard is an undefined behavior. So we have this example code here where you could see, okay, somewhere a guard is created and we forget about the guard. And by this, the guard doesn't get dropped. And when the mutex like is out of scope, nothing is unlocking it anymore. And the problem is if you have like an unlocked mutex and you call this destroy, or when you have a locked mutex, and then you run into undefined behavior. So everything could happen. Maybe everything is good. And so there was a solution given by Marabos, and I think that is something that was implemented for some time in Rust. Just use lock and unlock before drop, and in the worst case, you could also forget or leak the mutex, so it would be cleaned up after the process is killed, and the operating system would do this for us. Yeah. Whoa. So a lot of questions like what do we learn from this? So maybe just take a so what should we do? So we just learned like we have to it's really hard with this pthread C library to do Rust stuff. So the question is like, should we rewrite it in Rust? And I hear it a lot, and I got a nice post on Eurorust with some propaganda for it. And I think in this case, we can really have good causes for this, because it is a C library. It has like a lot of problems with the move semantics. So we had a lot of trade-offs to give in for that. So and if you think about the history, like some C libraries are from the 80s or 90s, and like move semantics, they were like introduced in C++ in 2011. Like I think that was the standard that introduced some. So some years before that, a lot of papers went out, and in C++, there's no borrow checker to protect you. You can get like move semantics, but it's really dependent how you implement like functions like the constructor and move constructor. And as long as you use nowadays C++ standard types like the unique pointer, there is a guarantee that when you move a unique pointer, the old unique pointer is null in the end, becomes a null pointer. And yeah, that's also true for std vector. So I think for every type in the standard library, but maybe not for types you use in like open source libraries or other parts of code. And in the end, and that is really what I see a lot in this legacy C code bases, there are so many pointers around and showing those stuff. So like just pointing around, and you're not really secure to move things. So for that reason, yeah, Rust is like a better fit, and we come to our next topic. So it's about the fast user space locking, futex, and there is also a lot of documentation in the Linux man pages about that. And they are actually used to implement the pthread. So we just go one layer below, and now we look how well can we do, which is like a good idea in a lot of cases. Okay. And on Linux, you can use a syscall with the name sysfutex, and it works with the address of a 32-bit atomic integer. And the main operations that we will see in this chapter are futex wait and futex wake. And they read only on this atomic integer. And all the scheduling and which threads are waiting, that is actually managed by the kernel internally. And yeah, so I also headed to the man pages, because if you're reading the book chapter, you find a much nicer signature there from the libc crate. But this is actually the C function we are using. So we use syscall and this futex, that is what we like, some kind of tag or enum that really identifies the syscall. Here we give in our the address of the atomic integer. And yeah, so on the second argument, we have like the futex operation in this case. And so on the next slide, I will also talk about other operations, but we will concentrate on futex wait and futex wait before that. And for those, these other arguments like value 2, uaddress 2, and value 3, they're ignored. But what is important, this is used in the wait case as an expected value, because we have like an atomic compare and wait function. Okay. So yeah, here it is. So this is now the first one was like the signature, just showing the general signature, and now we see here for the futex wait operation, we go for compare and block operation. So we block if the expected value, which is in this thing, is still the same as here. So otherwise we don't block. Yeah, and because the check is in user space with an atomic, it is quite fast, and we are not communicating with the kernel if we don't have to wait, which is like saving a lot of time in this case. And here we see like a small function that we will use in the example for waiting, where we just give a reference to an atomic and the expected value of the atomic. And the function is really just a wrapper for the syscall we saw before. And here you can see we hand in the atomic as a pointer. So we operate on the address in the syscall, and that's the reason why unsafe is needed. And the expected value, yeah, it's used to check before if we really have to sleep or wait at this time. And you could also give in a timeout for the wait if the wait occurs. Okay. Yeah, I think we did a lot so far. So that's it for futex wait. Now we talk about wake, and I'm absolutely sure that I pronounce it the other way around one time. So I'm sorry for that when I get you confused by that. So, and the nice thing about futex wake is we just we always have to operate on an address of an atomic integer. So that's true for every futex operation. But in this case, we just need one additional value, and that is how many threads we want to wake up. And mostly this is either one thread or all, like with this constant int max. So let's see. So on this slide, we have the wake one variant where we have similar structure. We wrap the libc call here, and then we give our atomic address. So here we work with a safe reference, and here we cast it to an address, and we believe libc create that it's performing correctly. And we also have to decide on the number of threads to wake up. And so with both of those functions, we can now have a main example. So we define an atomic which starts with 0. And now what we want to do is, like, we wait for some time, store 1 in it, and as soon as the 1 is stored there, we continue on the main thread. So what we do is, like, we use a thread scope to span a thread here. And in the threads, the first thing we do is we sleep for 3 seconds. And then we store the 1 in the atomic, and we call our function wake1 with the address of the atomic. And the nice thing here is, like, because of the thread sleep, like, that may happen first, but then it sleeps for 3 seconds. So we get into this loop second. So if we really think about sequential, and here we have a while loop. So as long as the atomic is 0, we wait, and we expect that it is 0. So and that is a nice thing. If this, like, if this would be like 3 nanoseconds or something really short, and the atomic had, like, time to change between this statement and this statement on the other thread, so this address would point to a 1, the expected is 0, and we wouldn't wait and wouldn't bother the kernel about it because we have the compare exchange before that. And after that, we print out that we're done. All right, I hope that was understandable. And yeah, maybe at this point, I give this outlook in the middle of the chapter, because I just want to get you fueled about the next chapter, because it's quite implementation heavy as far as I understand, because we will use this stuff to implement a mutex, a condition variable, and a read-write log. And I think there will be some optimization involved on the user space side, so I'm quite looking forward to this. But for my chapter, which is more like, let's say, we're in the chapter where a lot of knowledge is, like, flowing in, and we learn about a lot to memorize, maybe, and also quite interesting stuff, because there are a lot or many more futex operations. For example, the wait and wake bit set, and the requeue. And yeah, the requeue, it's like I would like to discuss this a bit with you. And this futex operations, they also have a flag. So you can give in a flag, which is called futex private flag. And if this is, like, used, you're telling the kernel that you guarantee that this atomic variable is only accessed from one process. And yeah, that's probably true in a lot of cases. So that is a good way to help the kernel to optimize, to be faster, given this information. Okay, but now let's look at the bit set variants. So this wait and wake operation on the bit set, they have an additional parameter, which is like, when you remember our signature, it should be pass3, I guess. And it is a 32-bit integer bit mask. So, and I think there was a nice example in Mara's book. She came up with this example bit mask, and just if the AND of the bit mask of those two numbers is not 0, we will perform the wake up. That means here we see these both will end up to be 1, be greater than 1, and like this here won't end up as a 1, and so we won't wake up because everything else is just 0. This kind of bit mask are actually often used in collision detection systems in games to like use just a small integer variable to group objects or collision primitives together. So that's a quite cool technique. Here in the book, there was a read-write log given as a example for what would be a use case for the bit set variance. But on the same time, it was like Mara was writing like, but when you use like 2 atomic values, that could be more efficient because like the kernel has a list for each of the atomics. So you would have like a list on all threads that have a read log and a list on all threads that have a write log. And so, yeah, especially if you like to, I guess if you like to have a priority on the writer, which is sometimes a thing, then going with the 2 separate atomic values variant should be beneficial. Okay, yeah, that's my arch enemy. And so we for futex req, which has a name that leads to assumptions. The first number of first argument is the number of threads to wake up, and the second argument is the number of threads to requeue. So if we wake up, for example, 1 thread and there are 3 other threads to open for requeuing, and we say we want to requeue all other threads, then this would like put the so it would let like this atomic variable be linked with the with a secondary atomic variable. So we have like this first atomic variable that was our U address, and in this variant of the futex recrack, we have a secondary atomic variable, which is used to requeue the open logs. So the use case that we're given here is like a condition variable and the notify all function, because even if you want to notify like all threads, you just would give the kernel a hint where that he can wake up every thread, but the kernel would decide and there would be a requeue. And yeah, I think so I started to read the man pages, and there was an example, and they also talked about the thundering herd problem. That is when like 100 threads would be sleeping, and then we wake all up. One of them will acquire a lock, and like 99 would just not get the lock and somehow fail. So you have this herd coming, getting a lot of CPU cycles wasted, and just one of the herd will get the lock. Yeah. And there was also this example given which is more C style code or C++ style code. Yeah, and in this example, like all waiters are waiting at the beginning for B, so they're blocking on B, and this future requeue then it would just wait one, which would lock A, and the others would start to wait on A without being awoken, because it's like in this case, if you have this kind of source code, that makes probably sense. And I was really trying to wrap my head around it. I think the condition variable, okay, but what I think is like this actually looks a bit like a queue. You could say here, this is like, why not is empty. And so I just bring this up for discussion. So, and then you would like check on the size of the queue, and after you unlock the size that is locked, you could see something here. We like a move of the data. So you move or pop the top element of the queue, and then when you stored it for like local thread calculations, you could start to log A again and redo the loop. But yeah, I'm pretty still a bit confused by this example, and yeah, maybe you have the idea regarding that. Yeah. So I think the slide just slipped in. There's another very important concept. It's called thread priority. And that is when like a high priority thread, so something that is really important, you change the priority on the operating system level, wants to acquire the futex lock. So, but the lock is actually owned, so a low priority thread unlocked it. The low priority thread gets no CPU cycles because there's a lot of congestion in your system, and then you wait for ages. So even also because the high, so you want like a functionality that says, okay, we have a thread priority, and this priority should be inheritant. Like here it is with, oops, where is my mouse there? Priority inheritance. There, in this case, the atomic integer, it is like getting a lot of state related for the kernel. And with this additional information, the kernel implements a priority inheritance. So as soon as a high priority thread wants to lock the atomic, all other threads who have the lock gets the same priority like this high priority thread. And yeah, for this also like big bit level encoding is used. Like we use the highest bit for a flag if there's a lock or not. So we have one bit left for like user state, whatever that is. You could encode like, is it a reader or is it a writer, for example? And then there are 30 bits that are internally used by the kernel just to store the thread ID. Okay. So yeah, what is really nice is besides giving all the infos about the futexes syscall, Mara did also publish a crate on crates.io, which has the types futex and PI futex for priority inheritance futex. And yeah, it's it has a much nicer interface and a safe interface, so you could have some fun to wrap it, but yeah, that's already done. And I think that's great. Okay. So yeah, what is open is like, we talked a lot about how things work on Linux, and there is not too much information about Mac OS. So the futexes core by its own is not considered stable, but so it could change in versions of macOS. But there's a full pthread implementation, but it differs from the Linux implementation in a way that it's using so-called fair locks, and that means, okay, first come, first serve in case of locks, and that's probably not too good when like you have different priorities on your threads for a reason and get like a high congestion in like your CPU is just working all the time. And the nice thing is on macOS there's this vendor specific your OS unfair lock, and it's a lightweight platform specific mutex, but like types for condition variables and read-write locks are still missing. So that were like the information on macOS on these implementations. And yeah, Windows. So I'm actually maybe that's good for a story. I actually attended oops, should go here. I attended the Rust for Safety Critical Systems workshop at Eurorust, and there was a company, they had really well-prepared workshop with a like you CI where you committed your tasks that were like Rust code for a real-time operating system, and that was then were executed on embedded hardware. Like this was all of this was working with with yeah, continuous integration over GitHub, and just awesome. And like I was quite happy in the end, but like my Windows PC, it wasn't working for it. Like I installed everything what that was needed, and then it doesn't work. It worked in the end when we just deinstalled and reinstalled Rust up, but it took us some time to find the solution. And yeah, I just tell you that to what I think is like yeah, Windows is always a special case with its passes and so on, and you find a lot of issues that's only Windows related. That's quite funny. Maybe I, as a Windows user, should do something to improve the ecosystems there. And yeah, let's see. But that was like totally off topic. Back to operating system primitives for concurrency. So in Windows, you have the so-called Win32 API, which also still has this name, even after 64-bit is like the standard. And there are a lot of really heavyweight kernel objects. Like you have a lot of operating system level stuff gets a handle, and you identify this and by a handle. And a mutate, you can use wait functions on it. You could also wait on a file to become like readable and stuff like that. But the drawback is like, in any case, this mutate, it interacts with the kernel, and that is quite slow. So the heavyweight kernel objects, not the best fit. What is nice is there are later write kernel objects like critical sections, they are called in the Win32 API. And this is like a recursive mutate. It has an init, a delete function, enter, try, enter, leave. And well, it was just called the other way because mutex was already, like the name was gone, right? For the heavyweight mutex. And yeah, until Rust 1.51, this critical section was really used to implement the mutex on the Windows side for Rust. And yeah, in newer versions of Windows, like Vista or Server 2008, a slim reader writer log was introduced that is also usable for mutex. Like you could do a regular mutex by just yeah, by just using the writer interface of the slim reader writer log. And what is interesting, there's no priority. So a writer has not a higher priority than a reader in this log. It tries to be fair, but there are no guarantees, which is like not very specific, I guess. But when I understand it correctly, it's like, okay, when the same priority holds, we should try to make a first come, first serve. Otherwise, we shift in the higher priority, or in some cases, we just do something else. So no guarantees. Yeah. And what is quite what can be quite like what can lead to like problems and deadlocks is when you have like a reader log, then a writer log, and then a reader log. So you have like recursive logs on reads, and then yeah, the system cannot get these sorted out. So, well, there were a lot of information about Windows, and it's not only because I'm using Windows. So in even newer versions like Vista and Server 2012, I think, there is also a condition variable added, and this can be used with a slim read write log or with the critical section by using different variants of those functions. And what did make me a lot that really makes me happy. Like, yeah, it feels like there's some communication between people writing like system libraries and programming language and the vendors of operating systems, that they really get their move semantics right and guarantees that, so that the newer Rust versions can use SRV log and condition variable from the Windows 32 API to just wrap it without a box and without those trade-offs to guarantee safety in any case. So maybe you think like this, when you remember this example here, where was it? Come on. Yeah, I think it was this one. Like, you think, okay, that's rarely happening, but I'm not sure, because people tend to do all the mistakes they can do. And actually in FFI code, you have to use stdmem forget a lot to move ownership from Rust to other languages, so that Rust doesn't destroy the reference when it's when it's forgetting about it. Like if you move a type from Rust to C, that's what you're doing. So yeah. Okay. Well, yeah, there's a lot to summarize, but I will go through it fast. So syscalls are slow because they have to go into the system kernel. Usually you should use OS-specific system libraries. There's a great libc to help you with access functions from libc. On Linux, POSIX is that's an additional standard. It's implemented and it includes this pthreads, which was like the functions we used or we looked at the first part of the book chapter. Yeah, pthread is designed for C, and we did suffered with this for some time, but nowadays we have better solutions. Yeah, we did saw the futexes calls for Linux and looked into a lot of them. So I think we will see them again in the upcoming chapters. Like in addition to pthread, so macOS also has this OS unfar lock as a lead weight locking primitive. And Windows has quite like a history, like it started with mutex implementations that was quite heavyweight, then new lighter weight primitives like the SVR lock and the condition variable were added. I think I didn't talk about that. Sorry for this. That's another good news. It's like a even newer version of Windows. We have function wake by address single and wake by address all, or wait on address, which is very, very similar to the futech function we did saw. So that was just me going too fast through the slides. So with that, maybe you heard I did start programming because of games when I was a teenager, and yeah, I think the Rust C and C++ Dragons community, we're looking forward to a game jam, and it's the beginning of December, and yeah. So with that, I would close this chapter and open this discussion. Thank you very much.
Awesome job. That was great, Tim. It's a tough chapter to cover, and I'm also especially impressed with how bang on time you are. Like it's a tough chapter not to go over on as well. It's an issue when you look at it. It's not so many pages, but each page is so dense with information that's not easy to explain. So you've done a great job. Let's have a look and see if we've got any questions. No questions so far. Just thank yous, many thank yous.
Oops. Oh, now everybody can see the chat. I hope that's okay. All right.
And if anyone's got any like observations or anything they want to share, like or how they're finding the book so far, then feel free to unmute yourself or post in the chat or anything. It's a tough chapter to have questions on, I think, because it's the kind of thing that you just want to like sit with yourself.
I had the feeling besides this requeue thing, which got me really confused when I started reading the man page. It was like a lot of knowledge to absorb, but like in these chapters about memory ordering, that was much, much harder to wrap your head around, I guess. So